Didn't she leave?
No, this is her last year though. Oh, she was sick. She was sick for about a semester. Yeah, so she was sick for about a semester. So it may have seemed like she left.
When I had her for last, she said she was like,
She wasn't going to. Then she did.
and then she did again.
Right. But now she's not coming back. As far as I know. But I was going to ask, so I know you guys had a sub on Friday. Would you like me, so here's my plan. So today I was going to either go back over what you guys did on Friday. All right. One no, a million yeses. Okay, so if I do that, if I back up and kind of hit the high points of that again, then Wednesday we will do regulation of the citric acid cycle, and I'll answer any questions that you may have for the test. I'm going to have you guys turn in today on the bottom of your quiz something I don't understand or want me to do again, and I will do that Wednesday, and then Friday's your test. And the test will cover glycolysis, citric acid cycle. Oh, metabolism in general, like overview of metabolism chapter, whatever that was. 13, maybe 12, 13, 14? That sounds right.
So 11, like just a little.
11 we.
Yeah, 11 was it was just a little blip. It was just fun facts.
It's not at all.
Just 12, 13, 14. So overview, glycolysis, citric acid cycle. So the stuff about carbohydrates is good in that you need to know how glucose is named and how it works through the cycle, but it's not going to be the main point of the test. Or on there at all, really. I'll just leave it off.
Will it be on the final?
There may be like a question on the final. Yeah, like identify the bond or which one's the chiral carbon and glucose, right? C1. So won't be anything. All right, in that case, let me back up a little bit.
How did she say it?
She thought it was great. So she thought she really covered all the stuff and it went really well.
We learned it all.
Even though all of us were like,
She did. She said she did go over very quickly. So we'll just go over it a little bit slower. And that's just a different style of teaching her.
oh, we watched this really great video too.
Yeah?
Probably
What video is that? A song? All right. Was it the thrift shop parody?
no. We tried to watch that one. That's like a million times worse than
I find that hard to believe. All right, so let's see. We're through that, enzymes. All right, so we'll just back up and go through some of the highlights that I have in my notes about these enzymes. Let's see here. All right, so as you're looking at your citric acid cycle, let me find my picture. All right, and here's our citric acid cycle. We've now done step 0. So entering our first enzyme is citrate synthase. So citrate synthase catalyzes the condensation of your acetyl-CoA, which was made in step 0. With oxaloacetate, which was you will make, made in your step 8. So it's going to combine a step 0 product with a step 8 product. That's where the cycle kind of turns over again. Citrus synthase is a enzyme that's found in a dimer form, which means it has two parts to it. It looks like a Pac-Man. Right, two enzymes where the active site is open until oxaloacetate binds. And then it's going to close around it. Oh, this looks like a cliffhanger. Conformational changes seals oxaloacetate into binding and shuts out the solvent. Yes. Which in this case is, what's the solvent in your body? Water. Good. You've never thought about it like that, but your body's primary solvent is water. Right, everything's solved in water. All right, so when it does that, it's going to shut out the water. And it's going to shut out the water to encourage this reaction to occur. If there was water in there, water would hydrolyze the bonds, and you wouldn't make the product you wanted. So by shutting out the water, it forces this forward reaction to take place. All right, so let me zoom in a little bit on that picture. All right, so here we have the oxaloacetate. It has a histidine that's reacting with an aspartate, as well as the acetyl-CoA from step 0. Right, here's our acetyl-CoA. And here's our oxaloacetate, which is coming in from step 8. So the aspartic acid does, what kind of catalyst would aspartic acid be, it being an acid? It's an acid base. Excellent. It's an acid catalyst, right? So it's going to take off a proton off the acetyl-CoA. That's going to force the acetyl-CoA to put a full-on negative charge on its carboxyl group. So now that it has that full-on negative charge here in step 2, it is going to attack the oxaloacetate, which is then going to abstract a proton from histidine. What kind of reaction is that? It abstracts the proton from histidine? Base, right? This is an acid step. This is a base step. So now acetyl-CoA has been bound to the oxaloacetate to make this citryl-CoA intermediate. So citryl-CoA is an intermediate that's stuck in the active site until the active site opens up a little bit and lets in the water. So the water and the citryl-CoA, it hydrolyzes the, let's see, what's the best way to draw this? It's going to hydrolyze that. Yes?
Do you want us to know like all of these smaller parts in between the big steps on here, or do you want us to literally just know it?
As far as structure,
Yeah.
you just need to know the structures of the intermediates.
Okay.
For this kind of thing, this is interesting because you've made a carbon-carbon bond without using a metal intermediate or metal to hold onto it, which you'll never see anywhere else in any of our cycles. So to know that this step is an acid-base catalyzed, and that you put in oxaloacetate and acetyl-CoA, you get out citrate and the free CoA. Those are the big things, and the big intermediate structures.
But you would want us to draw the mechanism.
I'm not going to ask you to draw the mechanisms in these steps, but recognize that, oh, I've made a carbon-carbon double bond, or carbon-carbon bond, right? I have joined 2 molecules that were not joined before, and I've done this without any sort of metal, which every time we've done bond, S-CoA bond. Every time we've done it before, we've needed some sort of magnesium or potassium or something like that to hold on to different parts of it to keep it from hydrolyzing.
So is this all step one, or is it one?
This is all step one. So
Okay.
enzyme citrate synthase does all of this. So now we have citrate, which was synthesized by citrate synthase, to send into the next step. And she told me that she didn't specifically give you delta G zeros, and that's fine, that's fine. You just need to know that it's, you don't need to know the specific numbers when we talk about delta Gs, but you should be able to recognize if the reactions are equilibrium, negative, or positive. The exact numbers don't really matter, but if it's easier to think about in terms of numbers, like, oh, this is really a negative value, then that is good. Anything else on this? Nope. Questions on that one? All right, let's get ahead then. All right, so now we're going to take our citrate that we just formed. It's going to interact with actonitase. Actonitase catalyzes the reversible isomerization of citrate to isocitrate. All right, so this is an isomerization reaction, so what would you guess the delta G should be? Should be right around 0. Right, because an isomerization reaction doesn't require any energy input. It's just rearranging where in this case, this alcohol has moved from carbon 3 to carbon 4. That's all it did, just rearrange where a functional group is sitting. All right, so then we've made our isocitrate. That is going to interact with NAD-dependent isocitrate dehydrogenase. Guesses on what kind of reaction this enzyme performs? A dehydration reaction. Excellent. So this catalyzes the oxidative decarboxylation, which means we produce a carbon dioxide. So this is our first CO2 that we have made, is oxidation. If it's an oxidative reaction, what sort of catalysis would you guess this is? Oxidative. Acid-base would be a terrible guess. What would be another guess? Redox is a redox reaction because you've done an oxidation. So redox would be an outstanding guess. So oxidative tells you it is a redox catalysis. If it's a redox catalysis, what cofactor are you going to need? 2 options. It could either be NAD plus or it could be FADH2. Well, it would probably be FAD, going FADH2. But since in the title it tells you it's NAD plus, that'd be the better guess as to which it's going to use.
Do you want us to refer to it as NAD?
That is its official name, but if you just know isocitrate dehydrogenase, that's fine. But if you know the whole name, then you're like, oh, I know that needs NAD+, which means it's oxidative, which means we're going to make carbon dioxide. So if that thought process is easier, which clearly for me it is, that's why I call it that, but officially its name is really just isocitrate dehydrogenase. Let's see. It's going to make an NADH and a carbon dioxide. Let's see what else. It requires this manganese 2+, which you can see right here. So we have this manganese 2+ in here to make the oxalosuccinate to prevent right, looking at all the options, there's a few places we could decarboxylate. The one that's leaving, right, this one off the side, or this one off the bottom looks almost identical. And so use that manganese 2 plus to cleave off the side carboxylate rather than this bottom carboxylate, because we need it to be a 5-carbon molecule to get to the next step.
You were saying it prevented something?
It prevents the oxidation of this bottom carboxylate. It's holding on to it, so it keeps it from being oxidized in the wrong spot. All right, so now we have made alpha ketoglutarate at the end of this step. So that is then going to head off and work with alpha, that should be an alpha ketoglutarate dehydrogenase. What was that for? Oh, sorry, let me look real quick. Let's see. It's on the positive side, around about 3-ish. Okay. So now we have made the alpha ketoglutarate that then goes on to interact with alpha ketoglutarate dehydrogenase. We're going to see another oxidative decarboxylation. So what sort of reaction would you expect? What kind of catalysis? Redox. And what should one of the products be? Decarboxylation means makes CO2. And again, we're going to use NAD to make NADH. So every time you see oxidative decarboxylation, think redox. Decarboxylation means carbon dioxide. The redox could be either the NAD plus or the FAD, either one. So it's a multi-enzyme complex that has an E1, E2, E3. What enzyme is this going to be very similar to? Pyruvate decarboxylase. So instead of having E1 be pyruvate decarboxylase, it's now alpha ketoglutarate dehydrogenase, but then it has the same 2 parts. So its mechanism is identical to step 0. So I'm not going to write it out because you already have it someplace else, but key fact.
Does it have like TPP?
Mm-hmm. Yep, it has all the same cofactors. It has TPP, it has a CoA, right? Because here we're putting on a CoA where we didn't have one. We're adding a CoA. So TPP, CoA, lipoamide, NAD+, yep, FADH2. FADH2. So it works just like it. It has all the same cofactors and is going to make a similar type of compound, right? We use step 0 to go from pyruvate to acetyl-CoA. Here I'm going from alpha ketoglutarate to succinyl-CoA. So this reaction releases carbon dioxide, makes a NADH, and more importantly, succinyl-CoA is a high energy compound.
You mean pyruvate dehydrogenase?
Oh, yeah. Sorry, I was reading D. Yep. Dehydrogenase. I do. So we've made succinyl-CoA, which is our high energy compound. What does it mean if the energy is going to be high energy? It can mean 2 different things. Yep, so it's going to need energy to make it. But then if I cleave off that CoA, what do I get out of it? A lot of energy. So the delta G to make it is going to be on the positive side. Positive like 3, 5, somewhere in there. but the cleaving of it is going to be negative, I think I have it over here, should be like negative 32. So it takes some energy to make it, but the cleaving of this produces a lot of energy.
So where does that energy come
Where does the energy come from? From the cleaving of it?
from? No, to make it, like.
To make it?
Driving.
The next steps. So we've had like a 0 and 2 pluses in a row, but the fact that later on it's going to be minus 32, it overcomes the 0 and the 2 small pluses. It's a coupling reaction, right? So it's all in the cycle. So overall, the cycle is exothermic. Individual steps are not, but the fact that they can be used farther down the pathway encourages them to be made.
So step D is considered positive, and then E will be negative?
Let's see. Yes, step E is a negative step. So step E cleaves this high energy succinyl-CoA to produce GTP. I'll explain this here in a second. Again, this is a 3-step reaction. I don't need you to know the exact 3 steps for succinyl-CoA synthetase, except to know that it's going to produce a free CoA. One GTP and one succinate molecule. So this reaction is almost energy neutral. It comes from the fact that the delta G so from cleaving that CoA, we get a negative 32, 33 kilojoules per mole. But to make our high energy compound, it takes about 30. So this step releases about 32. This step takes about 30. So it's enough energy to pull the previous 2 forward, plus make the GTP. So at this step, we're kind of back to energy 0-ish. All right, so we have now gotten to this part of the cycle, right? We have done 1, 2, what are we up? 1, 2, 3, 4, 5, so we're halfway around. So by halfway around, we've made our 2 carbon dioxides, we've made 2 NADHs, and we've just made our GTP. So then, using this succinate that we just made, we then use the enzyme succinate dehydrogenase. And its function is to catalyze a stereospecific dehydrogenation of succinate to fumarate. So this is an interesting molecule for a few reasons. Here is my malonate and here's my succinate. We actually looked at this way back when we talked about enzymes originally, a really, really long time ago. That malonate is a structural analog. Right, so the structure is similar. This is just 3 carbons, that's 4 carbons. So what sort of inhibitor would you guess this is? Competitive would be the best guess, right? Because they look structurally the same and they'll bind into the active site in similar ways. So this is most likely a competitive inhibitor. Succinate dehydrogenase contains an FAD bound into its active site. So what sort of catalyst would you expect succinate dehydrogenase to be? Redox, right? FAD should tell you it's a redox reaction. FAD is going to be used to oxidize an alkane to an alkene, which is what it's doing here, right? All single bonds to one double bond. So the FAD's job is to abstract one of these protons plus some electrons, 2 electrons, and make a double bond. And now we have FADH2. If you're thinking, I've never told you anything about NAD, I can tell you that. If this helps you remember when to use NAD+, NAD+ is used to oxidize So use NAD+ when you see an alcohol and you want to turn it into an aldehyde or ketone. It works better with alcohols or oxygen-containing compounds. FAD should only be used when you want to make a double bond. That helps you with your structure thinking, like when to use which one. Let's see, what other fun facts? Here's a good one. I'm going to abbreviate succinate dehydrogenase, not San Diego. Succinate dehydrogenase. Succinate dehydrogenase is the only membrane-bound enzyme protein in the citric acid cycle. So all the other ones are floating around in the mitochondria, running into their substrates and whatnot, moving around. This one is bound because, as we'll see in chapter 15, so we have just taken in 2 electrons to make FADH2. It will take those electrons and shuttle them through the electron transport chain to make ATP in water. So this is where the citric acid cycle interacts with the electron transport chain. They have a shared enzyme, which I'll leave you on a cliffhanger. We'll talk about that in chapter 15. Hopefully you can wait till next week. If not, you can always read ahead. If you can't wait that long, you can always read ahead. Let's see. Said that. All right. All right, so now we've made fumarate. That should be 0, because it's at equilibrium. Bless you, bless you. So now, fumarase catalyzes the hydration of a double bond that we just made in fumarate to make it a single bond, and that'll be malate. So looking at our structure, right, here's the fumarate we just made with our brand new double bond that we used FAD to make. In the presence of hydroxide, we make this carbanion intermediate that then can either come back this way or head this way and make malate in the presence of a proton. So, a few questions. One, what would you expect the delta G to be? 0, yep. What would force the production of malate in this? What would force this? It's not a great transition state, so I could go back to fumarate. So what would force this reaction to start making malate? So right, if the next step is running low, then it's going to pull the fumarate into the malate. So the only ways that you make malate is the next step needs it. Otherwise, it'll just flip back and forth. It's totally at equilibrium.
And then like the next step is ready for it.
Yes, when the next step's ready for it, it'll pull it forward. So our last step in the citric acid cycle is to regenerate our oxaloacetate. I realize I left a lot of space for fumarase. There's not that many things about it. So now we've regenerated our oxaloacetate. So I have my malate in the presence of an NAD+. What sort of reaction would you guess this is? Redox, excellent. NAD+ dependent. It's going to transfer a proton. So we have malate here. We're going to transfer a proton to the NADH, some electrons back to malate. So we've regenerated what we had was an alcohol, and now we have an aldehyde, which good, because 2 steps ago I said you always use NAD+. When you have an alcohol, you want to turn it into an aldehyde or ketone. Done. Making sure I'm right. Good, good. Guys, double checking on me. This step is not particularly favorable. It's delta G of about positive 30. But if you go back to the very first step, the delta G of the citrate synthase, that was negative 31. So it's enough negative to pull this step forward. So while this step is positive, the next step is negative enough to overcome this positiveness and still have a little negative left over to overcome some of the other issues. Okay, in my 10-minute recap, everyone feel pretty good about that? All right, let's look at some of the ways this cycle is regulated. So we've already seen one, right, with malate. But there has to be a way to turn the citric acid cycle on, off, real fast, kind of fast, real slow. And these are the 3 ways we regulate it. We regulate it based on the availability of substrates, right? So how much glucose is available, how much pyruvate, how much acetyl-CoA, how much of some of the intermediates, right? It's concentration dependent. The need for these citric acid cycle intermediates. So at each one of those steps, we make an intermediate. And so a lot of those intermediates don't stay in the citric acid cycle. They can be siphoned off to fatty acid synthesis, nucleotide synthesis, other systems. And probably the most obvious one is the band of ATP/GTP, right? If your body's needing more energy molecules, it'll push it through the cycle. right, so we already talked about this, the fact that when you send in one acetyl-CoA or one acetyl group, you're going to get out, you need, forgot the word pair. For electron pair process, right, you're going to need 3 NAD pluses and 1 FAD. But if we think back to how this is linked to glucose, one glucose makes 2 pyruvates, so those 2 pyruvates make 2 acetyl-CoAs, and each acetyl-CoA makes 3 and 1. So really, it's 6 and 2 and 2. So one glucose makes all of these products. Overall, it should make 10 NADHs, 2 FADH2s, 2 GTPs. And then this, chapter 15, when we hit the electron transport chain, we will turn all of these NADHs and FADH2s into ATPs. So one glucose should make, I think that adds up to like 40 something. 32. What is the key to making 32 ATPs? So right here at pyruvate, we had 2 options, right, of things we could do with pyruvate. If we went aerobically with oxygen, we head down this way. If I go anaerobically, I make a different path. So if you do the anaerobic, so you're working out real hard, that pyruvate lactic acid buildup is a dead end, and so you only make 2 ATP. There's no oxygen, so even these ATPs don't get made because you're going down a different pathway. Yeah?
Where did you get 32?
32, did I not add those right? Let's see here.
38.
I probably just added wrong. 38 cents. I had 38 in my notes, and I wrote 32 for no particular reason. Okay, let's do one more thing on this chapter. Actually, let me think. Regulation. No, I'm going to save it. I'll save all the rest of these for Wednesday. So, on your quiz, actually, no, I'll pass out some paper. You guys can write questions on that. I'll do that.